Dostał jakieś prezenty, które by go wyskakiwały.
So Gosia, are we ready to get started?
Am I ready?
Yeah.
Okay, welcome everyone. Welcome everyone to zkWarsaw Meetup 13. Today we have two pieces of news. News number one, we have an official announcement about two new sponsors joining our ranks. That is the Ethereum Foundation ecosystem support program and also VLayer, represented by a lot of people here. So thanks so much for for the sponsors. Other than that, and not completely unrelated, feel free to suit yourselves to a drink. Other than that, today we will have Leon tell us about arithmetization and how to transform a program like we know into something that can be expressed in polynomials and zk proof. So welcome, Leon.
So I'm gonna start with the motivation for this presentation. So usually when we start reading about zk proofs and zk in general, they focus a lot about how proving works under the hood. They focus a lot about how to make it more efficient, about how the commitments work and stuff like that. But when you start writing programs in a high-level language like Noir, it's much more important to understand how they're actually transformed under the hood to reason about the performance of that programs. Because there is a bunch of stuff that's happening under the hood, and this is what this presentation is about. So it's not about the proving, it's about bringing it from the user-readable code to something that can be proved. So this is the draft of what we're going to be going through. So it's like a plan for the presentation. But without further ado, let's just start. Some disclaimers. Sometimes I will tell partial truths here, because it's just easier to explain stuff when you don't try to be 100% correct. But yeah, if you notice something that is not correct or that is weird, just ask questions, and there will be some gifts for people who ask the best questions or participating actively. And
what are the gifts?
So I have some notebooks from the YouTube channel 3 Blue 1 Brown with mathematical quotes. So if you want to get a great mathematical notebook with some quotes on each page,
oh wow,
then yeah, be my guest. So when we're talking about zk, there is one thing that's important to understand. It's that writing programs, writing those proofs, entitles a paradigm shift. It's a little bit of a loud word, but we're not doing the computation, we're doing the verification. And it's different, but kind of the same. So our result is always Boolean. It's like success or failure. Did we verify correctly or not? And computation is part of the verification, because at the end we verify something, but before we can verify it, we need to compute it. So that's something to keep in mind, that instead of computing, we're thinking about verifying, and that has a couple of implications. For example, some parts are much easier to verify than to compute, and in our code, computation will be kind of like unverified computation will be for free, and we'll be able to leverage that in some places to do verification easier. So let's start with, I call it zkVM. So what we have available to us when we're writing zk programs. What is our environment, what we're working with? So we have basically, on the simplest level, two operations, addition and multiplications. And the values we're working with are field elements. So they're 255-bit numbers, modular prime numbers. So we just have numbers, nothing else. And we can add those numbers and multiply those numbers. And we're talking about, when we're talking about performance, addition is for free and multiplication costs 1. And our output is Boolean, true or false, because we can also compare values for strict equality. So we compute something, and at the end, we can check if it's equal to 0, or we can check if those two values are equal. So those are all the building blocks that we're going to be using for building our circuits, our programs. Yes?
So this is one specific proof system or arithmetization technique you referred to, right? Because addition doesn't need to be free.
Yeah. This is true. This is the first simplification. Addition doesn't need to be free. In other proof systems, it's different. I'm talking in general to give just like an understanding that additional in general is cheaper than multiplication. In Plonk, it's not like that, and we will be seeing the example for Plonk and Noir, in which the addition, in fact, is not free, but it can be combined with some multiplications to become cheaper, which we will see in the actual arithmetizations of actual programs. But if we're talking about growth, I think, and rank 1 constraint systems, then their addition is free. Yes?
So what do you mean by multiplication cost 1? Because the addition is just like the addition on the elliptic curves, but the multiplication is just the double and add algorithms or something different?
So currently we're not talking about elliptic curves yet. We just operate in this like environment where we have just like field elements, which are prime numbers modulo prime, and what does it mean to cost something? So at the end, our program will be a list of gates, and each multiplication will add one gate, but additions will be combined into gates, so there will be kind of free, but not in all proof systems. Yeah, so our output is Boolean, true or false, because at the end when we compute it, at the end we compare it to 0, and that is true or false, or we can compare two numbers together, which essentially is the same as comparing to 0, but just like subtracting them from each other. And we can combine those operations. So here we can add x to y and get z, but then on the next line we can multiply z by x, essentially getting z1. So our program will be a list of operations, additions and multiplications, and at the end we check that our result will be equal to the expected result, or our last step can always be in a form of zn equals 0 if we're just doing zn equals zn minus 1 minus value. So that's how we transform all comparisons to equalities to 0. And we can also do unconstrained computations. So we can use the unconstrained to compute something which is not verified, and then use the result of that computation to verify our computation. And that will be helpful in some cases, because for a bunch of computations it's easier to verify against something than it is to compute this something. But we'll see that in the next example. So when we talk about zk, we're talking about like circuits, and when you ask yourself what is a circuit and why do we even call it a circuit, this is a graphical representation. So we were talking about those operations here, and this always had like left element and right element and output, and here was the operation, multiplication or addition. So in general, we call those lines gates, and here is the example gate. So it has always the left element, the right element, and the output element. We call them wires, left, right, and output wire. And in this gate, we have the operation, which is addition or multiplication. And there is some mathematical statement that says that each program can be represented as a tree, as a DAG of those gates. But we'll see later how they can actually be represented. So yeah, when we compile this program, it gets, this is not the correct arrow, but I'll remove that later. But it's similar to, we take the program and we compile it to something like that, which combines those values using multiplication, then compiles those values using multiplication, and then those values using addition. So we combine, compute, and then verify at the end. And this is kind of similar in a way to how processors look. So they also have those gates interconnected together, and that's why people call it circuits. It's my understanding, because of the similarity to the processors of those trees. But this is actually not implemented in any real processor. It's a software implementation. So here are some of the examples of the circuits representations for some polynomials. Why are we talking about polynomials? We were just talking about programs, because there is a statement mathematical that says that each program can be represented as a polynomial computation, but it can be inefficient. But we will show how to represent programs as polynomials, and then polynomials can be easily computed using those addition and multiplication operations.
One question.
Yes?
Is the transformation into a polynomial inefficient, or is running the program as a polynomial inefficient?
So sometimes when you take the program and you transform it into a polynomial, it's just a huge polynomial when the program in itself is simple. And that is a problem because the things that are efficiently represented with polynomials are different than the things that are efficiently represented in code. And some things that are easy for us in code are actually very hard in polynomials, like bit operations or something like that. Because we have like different arithmetics here and there, and because of that, sometimes we have an incomparable complexity. So we take something that looks easy, we transform it to polynomials, and it's like a huge polynomial.
And there are any golden rules how to create those
We will
some best practices kind of.
yeah, we will start now and build some of the primitives from the bottom up. This will be the whole core of the presentation. We will show how to express this as the polynomial, how to express this as the polynomial, and then we will express most of the programming concepts that we need.
Thank you.
And how can you express non-deterministic programs in polynomials? It sounds...
You can't express non-deterministic programs as polynomials, and we will, I think, and we will only show the deterministic programs here. Because in the circuits, it's similar to solidity how we say we do deterministic stuff here. And I think like you can put some non-determinism outside, so like you can provide the inputs that are non-deterministic, but the computations on those inputs are deterministic. Yeah, so we will show some of the examples just to understand how the circles work. This slide is mostly to demonstrate a couple of things. So this is the computation for this polynomial, x1 and x2, and it's squared. So we take this squared, and this 2 times squared. This is from the binomial when you take this out. We could actually do it more efficient here if we just take the sum and then take the multiplication. But this does it from the formula of x1 squared plus 2 x1 x2 plus x2 squared. So this is x1 squared, and it shows that you can actually connect left and right wire to the same value. So they do not necessarily need to be connected to different values. And here, this multiplication, it shows 2 here, but actually this will happen here because you can, in the same gate, do multiplication and multiplication by constant. This is just a simplification here. This is...
I don't know if it's obvious, but in the second row, it's the x means multiplication, not the x line.
Here?
Yeah.
Yes. Yeah.
So it's not a variable, it's an operator.
Yeah, x1 is a variable.
It was a little bit confusing for me in the first moment.
Yeah. This is the second this is the second variable way to represent the same computation. So we take x1, x2, we take the sum of those, and then we just multiply it by itself, which kind of shows that we can create intermediary variables and that our circuits build from more and more complex stuff. And this one computes the polynomial which has those roots. So it takes 1. You can put the constants in here, and it takes those roots and it multiplies them and then adds them and then does a multiplication. But this is more a theoretical example. We'll jump to more practical now.
What is the difference between example 1 and second example 1?
They're computing the same value, but they're computing it in a different way with different intermediary steps.
And which one is cheaper?
So when this second one is cheaper because second one has 1 multiplication, and this one has 3 multiplications. So this one will take 3 gates, and this one will take 1 gate. So if we can combine, so yes.
And on the example 3, the gate that multiplies is going to be like really heavy, right? Because there is a lot of multiplication.
Yeah, this is not fully correct because it will have n minus 1 multiplications, and here it's written as 1 gate, which does n minus 1 multiplications. I took those examples from the internet, and I should have redrawn them because they are confusing. We'll do better next time. So
Because of binary inputs, right?
because each gate only has left and right input, yes.
So it's the same for the left example, right?
Yes, exactly. But here it's an addition, and for addition it's less critical. But for multiplication, this is a critical thing. So when we're talking about the circuits, it's important to understand that depth doesn't matter. It just matters how many multiplications do we have. Depth is in a way affecting the number of multiplications, but in general, when we think about computation, We don't think about how deep is this tree, so if we make it wider but shorter, it doesn't change the performance. What changes is just the number of multiplications. And those DUGs as direct acyclic trees, because as we've seen before, this does not necessarily need to be a tree, this is a DAG. We cannot have cycles because we cannot have variables which depend on themselves because we cannot then compute them. Yeah, so those DUGs are cyclic, we can have, and that means also that we can't have arbitrary length loops because then we will need to cycle and cycle and cycle. And they can be large, and they're usually large for real programs, but they always need to be bound in size because this structure, like the structure of a program, is static. As we see here, the structure of a program does not depend on the inputs. So from that, we see that we cannot have like conditional jumps, and we cannot have variable length loops. But we will go over that, and we will have something like variable length loops built later, so we can actually express some of the stuff that we want in our programs.
Can you give a very quick idea on actually the complexity? So, for example, I have example 3 and I add more multiplications, etc. And what does it do to my circuit in terms of complexity? So therefore, how long it actually takes to compute it on, say, on a standard architecture?
Mm-hmm.
So without even invoking GPUs, etc., just just a MacBook Pro, for example.
Yeah, so for those simple examples, it's very fast, so it doesn't make sense to talk about complexity here because here we have like 3, 5 gates, and all of that is instant. It's just like how fast can you start your binary program. But I can give the examples, the real-life examples of stuff we are working on currently. So we, for example, have hash functions. We use Keccak-256, which we compute in circuits. And we compute this Keccak from some variables that are of the length 500 bytes on average. And that takes 250,000 gates to compute. So this hash function from one layer of the proof in the Ethereum. So we're doing that for the Ethereum storage proofs. And the other example, yeah.
So what's the overhead? 1000x, roughly?
The overhead for Keccak?
No, for doing a ZK. So when compared to native execution.
I
Heavily depends how arithmetization friendly is your code. Right?
Yeah.
So for example, bitwise operations are completely unfriendly, and addition and multiplication is super friendly.
And for your hash implementation, Keccak implementation?
Keccak implementation is very unfriendly because Keccak does a lot of XORs and it does a lot of ANDs, and those are bit operations. And we will see how to do bit operations later, but in general, some of the operations are surprisingly hard on ZK. For example, if you want to take those elements and compute if they're equal, that's easy, you just do it in one operation. But if you take 2 elements and you want to compute this one is less than this one, then it is surprisingly hard. So it depends on the structure of your program, and that's kind of what motivated me to dive into this and to look how compiler actually does it, because I'm writing a program and I'm running the compiler and it tells me, oh, it takes X gates, and I'm like, why? And what can I do for it to take less gates? And that is completely non-obvious, and I haven't seen any good documentation on it. And it also depends on the version of the compiler, because they do improvements and they introduce something called lookup tables, which optimize functions which are non-trivial to compute, and they introduce custom gates, and all of that changes the performance and improves it, but in non-obvious ways. So I wanted, when I want to reason about the performance, I wanted to at least see like, oh, can I divide 2 things and are they addable? So if I have this part of the program and this part of the program, like, do they somehow get combined together within the compiler, or are they completely separate? And for example, I saw that if I compute hash 2 times in a program of the same variables, then it's actually the same cost as computing it once. So under the hood, the compiler does some optimizations and shows that this code is the same as this code because it has the data and it can do optimization based on the data. Yeah, and then if I compute, for example, the hash function, and I change the last variable in the hash function, then because hash function is based on blocks, and the variable of the first block will not change and the second block will not change and only the last block will change, that is actually also faster than computing just 2 completely separate hashes. So those were some interesting findings, which are not in this presentation. Uh, yeah, but we'll show some building blocks now. So yeah, any computation can be presented in this form, but it can be very inefficient. But we will show now some computations that can be presented quite efficiently and that can be understood. Because in practice, when you write Noir and you compile it, usually you get thousands of gates, and it's very hard to understand what those gates actually do, and how can you decrease their number or do anything to understand it. So the best way I know going about it is to like go from the bottom up and understand more and more complex programs, and that's what we're trying to do in this presentation. So we'll start with the trivial programs, understand them, and then go deeper. So the simplest program that we can, simplest is actually like check that A multiplied by B is equal C. But we will here try to check that A is the modular inverse of B modulo P. And the way we will do that, we can do that in two ways. We can use the small Fermat theorem and just do multiplications to raise A to the power of, actually raise B to the power of P minus 1. Yeah, but I should have written that differently here. So our goal in this is to compute the B, but the trick is that instead of computing the B using the little Fermat, we can actually compute the B in unconstrained code and then just check that it actually multiplies and it gets the B. So this is the trick that will be useful in other codes, so that we can do some stuff in the unconstrained. Stuff that we do in unconstrained is completely free, but is completely unconstrained. So, which means that a malicious attacker can like substitute any variable there. So stuff that you get from unconstrained, like it could be good, but it could be bad. So you need to check everything about it later. But here we're good because it is the check. We're checking everything. So if this is correct, then we know that stuff that we got from unconstrained was correct. So if malicious attacker inserts some bad variable here, this will just not be true, but this is constrained. So this is the first operation.
I
And
think it's worth mentioning that it's basically a division, right?
yeah, yeah.
Because it sounds very complex when you say
Yeah, so we,
inverse of.
yeah,
But
so
in practice, if
it's
you
a
want to-
division. So we had the multiplication as our base operation, but if you want to do a division, you think, oh, is it more expensive? And I check in the compiler, and the way compiler does division is it just does division in unconstrained code and does one multiplication. So that's the answer for the question, how much does division cost? 1, because it's a single multiplication. But it increases the prover time because it needs to do this unconstrained computation, but it's very quick. So, because this is just like a division on a normal processor, so it doesn't do any crypto stuff on it. Crypto stuff is on the unconstrained operations.
What does this unconstrained line do? Like, not this line, but just what does the keyword do?
So this is a pseudocode, kinda, but in Noir you can have unconstrained before a function, which will mean that the compiler under the hood will execute this function and will insert the result of the execution of this function into the code that's calling it, but it will not include the operations in these functions in the circuit, so it will not try to prove the execution of this function. And it's much cheaper to execute the function like a normal function in normal code without proving it, because proving is a computationally expensive process that we will later call on our circuit, and proving time is linear to the number of gates, so we're trying to have as little gates as possible, and the number of gates is our performance metric that we're tracking. So this is, let's say, reversed keyword that says, do this without proving this, and then insert it, and we'll prove the result of it. So now we will check that x is a root of this polynomial, and we will see the concrete example with x equals 1. We can, again, compute it two ways, either a naive way of computing this and then computing the minus, or we can see that this polynomial is x multiplied by x minus 1, so it has roots of 0 and 1. And this is how it will look in arithmetization. So we first multiply x minus 1, and assign it to x1, and then we, not multiply, but compute x minus 1, and then we multiply x1 by x, so we're essentially computing this, which is the same as this, and then we check at the end that the result is equals to 0. This is our check for equality to 0, which is always at the end. And this is the same with the concrete values, x substituted for 1. I do this because later I will show for real programs and real input values and real compiler, also gates in this format and gates in this format, so we see the values as they flow through the circuit. So we first do 1 minus 1, which is 0, then we multiply 1, which is x, by 0, which is the result of that, and then we compute that our result is 0, so that's correct. And now, as we can check that x is the root of this polynomial, we will check that x is a bit. So a bit is a value that's either 0 or 1, and we can see that it's essentially the same task, because this computation is correct only if x is 0 or x equals 1. So it's essentially the same computation as checking that x is a bit. So now we can, this is important because we don't have like bits as built-in types. We have just field elements, which are huge, but they can contain values of 0 and 1. And it's important for us to be able to represent the bits, because later we can express other operations when we switch the number into the bit representation. So now we can check if x is a bit, and now we have the exercise for the group. So if we want to check if x is a ternary bit, which is it's either 0 or 1 or 2, how would we do that? If we, for example, operate on a computer which has bits of not 2 values but 3 values. There were some computers like that in the early ages.
We would need to construct a polynomial with 3 roots, 0, 1, and 2.
Yeah. And we can
Times minus x1 times x minus 2.
Yeah. And we can use this trick to check that x is within any finite set, for example, in linear number of multiplications, which is not something you usually do in programming, but it's a trick that we can use to construct some weird computations. So this is it. This is this polynomial. And now we can check that B0, B1 is a correct binary representation of x, where x is less than 4. This is like, So we will do that by first calling the unconstrained code to get the B0 and B1. And instead of computing, instead of doing those divisions and modulos, we will call the unconstrained code, and then we will check that this is actually the correct representation of x. So the idea here is we will call the unconstrained code here, and then we will assert that B1 is a bit, which we had on the previous slide. We know how to do it. And then we will assert that B0 is a bit, and then we will check that B0 multiplied by 2 plus B1 minus value equals 0. This is the trick that we'll see a lot. The actual compiler uses, that's why I'm getting you used to this notation of not having value here, but having value here. And what if x is more than 4? Then it will be impossible for unconstrained code to produce us something that will satisfy those 3 constraints. So we don't need to check that, because unconstrained code cannot produce something that will satisfy those. Range checks.
I didn't get the last part. Can you say again?
Yeah, so here we call the unconstrained code. I need to add it here. But unconstrained code is untrusted. So what if someone gives us the results that are wrong, and actually x is more than 4? But then we will not be able to pass through those checks, because those checks are constrained. So if someone, for example, this is all constrained code. Before that, we have unconstrained, which computes B1 and B0. So for example, if someone in unconstrained gives us B0 equals 5.
So the function here has 3 arguments, B0, B1, and...
You can write it in 2 ways. You can either have a single argument value, and then B0 and B1 will be computed at the beginning of the function unconstrained. Or you can have, 3 arguments. So you can use this trick to do general range checks. So range checks for x. So You can do the check here. We check that x is less than 4, but you can check that x is less than 8, less than 16, and in general any power of 2 with the same trick, but just like a longer bit string. But now we will talk about the ifs. So ifs are very important at programming because before that our programs were just linear and just doing like simple polynomial computations, but haven't seen any progress without ifs, and ifs are weird in zk. So the way we express ifs, because we can't jump around in circuits, we can just compute stuff. The way we model if is we compute both the left side and the right side, and then we combine them together using this trick. So this is the predicate, p. So we compute the Boolean value of the if, and we get here 0 or 1, and then we multiply the then value by p, and the else value by 1 minus p. So if p is 0, then we will get 0 multiplied by then value, plus 1 multiplied by else value, so we will get only else value. And if p is 1, then we'll get only this value. And there are some important implications of implementing ifs like that. First one is usually when you write an if in a programming language, you expect it to behave lazy. So you can expect that if then is executed, then else is not executed. And in zk, unfortunately, it's not the case. You always execute both, and then you just multiply the result of one of them by 0 and the other one by 1. So that obviously has its performance implications. But the other implication is usually you can make assumptions in your code about the condition being true. So you check, if I'm within the bounds of the array, then do something with the array, but if I'm out of bounds, then do something else. But here the problem is that your code that does something with the array will also execute when you're out of bounds of this array. So you need to handle this case, and you need to write your code in a way that like always doesn't go out of bounds of the array, even when you're out of bounds of the array. How to exactly do that, that's more of the programmatic exercise, but it's something like to think about, that your else executes if your if condition is true, which is weird when you first encounter it. But this is because, yeah, that's the only way known to me, maybe not to society, to implement an if in as a polynomial.
And I have to ask a question. I have understood what you have said, but I have completely no idea why there is no way to check p before calculation of the circuit.
How would you do it?
You would need to run the whole
If
program.
you go back to a
prepare
slide with any of the gates in a graphical form. Yeah, so look at those gates, right? This is the only building blocks we have is addition and multiplication gates.
Aha.
We don't really have any
Okay.
other building blocks. So when you evaluate, when you put values in the x1, x2, right? When you say, okay, I'm gonna evaluate this gates, these circuits with those x1 and 2, it automatically implies what value is gonna be in every single gate, right? So it's like you cannot just say, yeah, we're gonna evaluate just 2 of those gates out of 5, right? There is no building block that allows you to stop propagation of evaluation in the circuit, right? Hence you evaluate the whole thing or nothing. Hence you need to execute both positive and negative result of the condition in the if.
So we function like a simple recursion with one if block. It feels really heavy, right? We like expect it to be kind of cheap, but it's really heavy in the circuit. Right?
Yeah, it's really heavy, and you also need to have a limit on the number, because if you do a recursion with like arbitrary number, then it's essentially an arbitrary length loop, and it will make the circuit infinite, and we can't have infinite circuits. That's one of the important things about circuits. They can be huge, but they need to be finite. So you need to like have the structure of them be, so the program needs to compile to something that has a constant structure. And
so
if the
dynamic arrays and stuff is like not really the option here, right?
no, dynamic arrays are not an option.
Okay.
Usually the way you go around that is you say my arrays are maximum 100 elements or something like that, and then you do everything for 100 elements, and then if there are 10 elements, well, too bad, you did 100 operations. Yeah, so we're talking about ifs, which is the first interesting stuff that happened here. Is they're controversial. Loops are much less interesting because if they're constant length, then you just linearize it, and it works just like that in the compiler. So if you have a loop of like 100 iterations, it just copies it 100 times and does nothing else. And if they're variable length, then, well, too bad, out of luck, you can do that. But you can overcome it with an if inside the loop sometimes, but you need to have an upper bound of the length of the loop. So if you want to iterate up to some variable, you can like check the if and then do something if you're still within the variable length loop while being in a constant length loop, and do nothing otherwise, but it will have its performance implications as, yeah, you compute everything if you don't need it even. So now we can think about how can we approach implementing A is less than B, because this is like a simple operation that we want to have in each program, but it's very non-trivial in Noir and zk because you can't have less than in our proving system or in elliptic curves or stuff like that. And the proposal here is to look at those numbers in their bit representation and use ifs, which we just constructed, and do something like that. So this is, again, the pseudocode, just to understand it. So let's say n is known at compilation time, and n is like the highest value of the power of 2 that those numbers are less than. So let's say if they're arbitrary numbers, that will be 255. And then we, in unconstrained code, we split A and B into bits. And those will be like arrays of the size n. And then we check if the first bit is less than the first bit in other number, then we know that the first number is less than the other number because, in the binary representation, if you have here 0 and here 1, it's obvious you don't need to check any other bits because it's less than. But then if it isn't, then we need to handle the equality. Do we? No, we just check the if. So if it isn't, then we check the first bit, and then we check the second bit, so on and so forth. And if there are no bits at the end, that means that we're not less than the other number, and we return false. But if you actually like unroll all of that into this polynomial with ifs, you see that it's non-trivial. And you can check it in Noir. You can just say a less than b for 2 numbers. It will complain that those actually cannot be fields, because you need to first cast them to some unsigned type. We haven't talked about unsigned types in Noir, and we haven't talked about Noir, but basically the way unsigned type works is the same. So it just says, okay, now instead of having a field element, a number, we have the bit representation of a number. And yeah, comparison of 2 numbers, it's quite expensive, but it depends on the size of those numbers. That's because of this 2 to the power of n. So if I want to compare u2 to u2, so like this unsigned numbers with 2 bits each, that's much cheaper than comparing u4 to u4, exactly because of that, because that's what it kind of does under the hood. Actually, this is like the idea how to do it. I'm not sure Noir does it exactly like that. It seems like that on the asymptotical levels, but the way I dug into that is I printed the circuits that I'm getting from Noir, and I tried understanding them. And I like understood the circuits for ifs, and I understood the basic circuits for like addition, multiplication, some constant operations, and for the loops. But when I tried to understand the circuits for those unsigned integers, I didn't understand exactly what's happening under there, but I saw that asymptotically they're similar to this solution. So I assume under the hood they probably do something like that.
Do you get some syntactic sugar for this
Yes,
stuff?
yes. This is not how you do that in Noir. This is just, so this syntactic sugar is those unsigned types in Noir. You can just define like something U32 and then work on those, and those can be easily compared. But yeah, you add one comparison, you get like 2,000 gates, and you're like, the hell.
In this case, I think that after this unconstrained computation, we need to make sure that this a bits is a correct representation of a.
Good catch. Yeah, we need to do that. I forgot about it.
Come again?
here, yeah.
Yeah, after this unconstrained computation of a bits, we need to make sure that this a bits is a correct representation of a, because these split bits can just give us some incorrect values.
Yeah.
And there is any preferred data type for A and B for those kinds of operations, or does it matter? Is it hex or?
So A and B are numbers here, and usually in NOR you get something as field elements, and then you cast them to signed number elements or unsigned numbers, and then you do operations on them. Because for example, if you want to
That means casting is quite expensive, no?
Yeah.
Because
Yeah,
then
and
you need
how
to
to
do a
cast?
range check on all the bits.
It's casted by compiler, or who is responsible for that?
It's casted, yeah, by compiler. Actually, there are a couple levels here, what we can call compiler or what we can call the prover system, because the way it works is like on the left we have Noir, which is a program that, let's show some Noir code. Yeah, so this is kind of like Noir works. So this looks like a normal program, or let's show an if. Yeah, so that is Noir. And then when you compile Noir, it shows you the number of ASIR opcodes and backend circuit size. And ASIR opcodes is arithmetic circuit intermediate representation. So it's, let's think about like LLVM. So it's not processor instructions, but it's some intermediate representation that later gets compiled to the circuit. And this is the size of the final circuit. So this is like our number of multiplications and what actually gets proven. This number is not very useful because some of the ASIR opcodes are very high level. For example, you have an ASIR opcode to do a range check, which is like thousands of instructions or hundreds. Or you have ASIR opcodes compute a catch-up hash, which is hundreds of thousands of instructions. So sometimes you have a program which has like one here and millions here. So that is not very useful. But yeah, so when we have the Noir compiler compiles something like this to those ASIR opcodes. And ASIR opcodes can be proven using different proving systems. So the one that Aztec uses and Noir ecosystem is called Barettenberg. But this is general enough that this intermediate representation can also be proven using other proving systems in theory. But currently they support just one backend. And this is, we'll talk about it later, this is how gates look like. So gates are just like those polynomials that equal to 0. And this will equal to the number of gates minus 5, because there are 5 dummy gates here that just do some setup. We'll not go into it.
And could you repeat where you have mentioned LLVM, and could you repeat where is on this slide LLVM?
Yeah, it's I'm on the fence if it's a good idea to mention LLVM to explain it here or bad, but like it's like compiler designers, like they don't compile their code now to the machine code, but they compile to LLVM, and then the LLVM developers compile it to machine code because it's much easier to do optimizations on that level. And here it's the same idea. LLVM, it's not used here. They have their own intermediate representation, which is called ASIR, this arithmetic circuit intermediate representation. And yeah, it's how you compile the Java to the Java bytecode, and then you execute it on the actual computer.
When you compile a computer program, you can compile it to assembly, and depending what processor you want to run it on, it's going to be different assembly, right?
Yeah,
so you have one compiler.
I was not sure whether NOR is using LLVM.
No, it's just an
No.
analogy.
Just an
But
analogy.
the point is you have different backends, and different backends can use different elliptic curves, have different mathematic properties, might be fast, you know, some might have fast recursion, some might have fast something else, right? So
Yeah.
depends.
There are also, like, the interesting part about the design of this thing is they have like opcodes for some popular cryptographical operations, but some backends might not implement them natively. So for some other backends, they might implement them within the compiler, or some backends will have them implemented. This is not important. What is important to understand here that this number is meaningless and this number is meaningful. But actually, the fun fact, Noir recently added a profiler, which is not useful because it shows you the number of those operations. So when I profile my code in VS Code, it goes to the line with my catch-up invocation and shows me this is one. One of what? Yeah, and here I have millions, and here I have one, and let's be happy about it. Yeah, so here we talked about the basic operations. So to sum up, we did the modular inversion. We did check if something is a bit. We used that to do range checks. We talked about how if works, how loop works.
I have one question.
Yeah.
How expensive is range check on U32?
U32?
Yeah, how many gates? I mean, roughly. Is it tens, hundreds, or thousands? Or
Let me check that.
because it seems that
Live demo, great.
Yeah.
because it seems it's gonna be very expensive, no?
Let's say we have U8 comparison here, not U32. Have two U8 numbers, and do we have here? Yeah. Uh, uh, 57.
So that's U8.
Huh?
That's U8.
That's U8,
Yeah,
and we
that's-
can check it now with
Two range checks and something, right?
U32.
Yeah, but maybe not. Maybe us at x equals y, but then because we don't know how many comparison types.
Do we have like 3 range checks here or just 1?
I believe that's two range checks.
Well,
There's
because
proof.
we need to constrain the x, that is really U32. We need to constrain y, that is really U32, and the assets, right?
Correct. So we have two range checks and comparison here. So maybe let's remove comparison and then we divide it by
Okay.
2 and agree that's the final.
So
Close to the final number.
yeah,
Instead of
we can experiment. The problem with Noir in general is that it's very eager to remove computations. So when you compute something and then don't do assertions on it, or do assertions only on parts of it, it sometimes
yeah, but the comparison is like 1 gate or something, right?
yeah, it 2748 here, and before we had 2752.
Okay. So
4? That is interesting.
comparison was pretty cheap. So
Wow.
okay, let's say the order of magnitude of 1000 is a single range check on U32.
Okay. This is the part I don't understand yet, because I was playing with U2 and I didn't even understand how it works for U2. Maybe we'll do that for the next presentation.
I mean, that's true. That answers my question.
Uh,
No,
oh.
no slides anymore. So it's crazy how expensive. It's crazy how expensive the range check as it goes into more bits.
Yeah.
It really lets you think, okay, we should really use as little bits as possible.
Yeah.
And when we like have the U32 arithmetics, we always do the range checks if we didn't overflow or something.
To be honest, it's not, because when you think about it, ZKs are on group operations. So mathematically, it's multiplication, addition, etc. So when you try to convert a range into what actually happens mathematically at the algebraic structure level, is something that is really weird. Okay.
Yeah,
The group cannot understand it. Okay.
Absolutely. But then, yeah.
And that's
Just
also
think
why,
about it.
sorry, just going why, when you try to extend on those techniques, regardless if it is a Plonk, bulletproof, etc., and you try to move, for example, in FHE, full homomorphic encryption, why it never scales. Okay, it's
Even worse.
it's even worse. Yeah, it's even worse than ZK keys. So.
Yeah, so as you've seen, I've modified the compiler to, so that's the fun part. The compiler currently, it produces this intermediate representation, so it produces that, but it doesn't produce this. The compiler only produces this on the fly when you ask for a proof. So when I wanted to understand something about gates, I just needed to go into the compiler and subconsole logs for it to show me the circuit, and then process this circuit in a sensible language. So yeah, we can play with that later, but this is how I got those results, but this is not this slide yet. Let's go back. So the Plonk gate. So because before that I told you that we have multiplication and addition, and 1 is for 1 and 1 is for 0, but it was like a very simplified understanding of how this VM works, just to not overload our brain with thinking about how it actually works. But in the actual systems, it's a little bit more complex. This is the form of the original Plonk gate. Currently, for the Turbo Plonk and Ultra Plonk, it has some more things, but the core is still not changed. The core is the same. And let's look at what's happening here. So what's happening is we have the left wire, XL, the right wire, XR, and the output wire. And we also have the constants on those wires. So those constants can be 0 or 1 to enable or disable those wires, or they can be actually like constants to do multiplication for constant in the same wire. And here we have multiplication of those. And here we have an addition of the constant, which allows us to express any like operation, any gate, addition or multiplication, or some more complex in a way with this polynomial. And the whole program in Plonk is a set of gates like above. And the prover proves two things, essentially, that all constraints are satisfied, all constraints are equal 0, and the copies on the wires are done correctly. So this is called the copy constraints, because here I produce something which is XO, the output, but then in the next gate, I use the output of this gate as the input of some other gate, so I also need to prove that those variables are actually the same. The way that copy constraints work in the prover is out of scope for this presentation, but you just need to know that these things are proved, so that if you produce something here and it's used in the same gate, it actually is all interconnected together and you cannot cheat there. So let's express our basic operations as Plonk gates. So if we want to do addition, we just say QL equals 1, QR equals 1, and QO output equals 1, and all else are 0. So then we will essentially have XL plus XR plus XO. It should be minus 1 here. So like equals XO, so this should be minus 1. This is a mistake. If you want to do an addition of constant, then you say QL is 1, so you take XL once, and QC is this constant, and QO is minus 1. Yeah, so this like equals QO. And if you want to do multiplication, you just set 1 to, this should be minus 1, to QO and QM. I was just thinking about it like what's enabled, what's disabled, without thinking about plus minus ones, what's on the left side, what's on the right side. But yeah, it's maybe even more understandable like that. So here we have those three things enabled, and here we have just this enabled and this for the constant, and the output enabled, and here we have the multiplication term enabled. This is like one term that allows us to do one multiplication. And yeah, you see that with this gate, in general, we can add one addition and one constant addition to each multiplication for free. Because like here we do the actual multiplication, but we can also set QC to something, and we can also like add one of those variables that are used within this multiplication. So here it starts to become harder to reason about performance, because this gate is like in some format. So you can't say just like multiplication is that and addition is that, because it depends on the ordering of the gates, what can you combine and what you cannot.
So what's the motivation behind using a Plonk gate versus a more simple one?
I think it is a trade-off of, if you use a simple gate, then you have more gates, but they're more understandable, but also they're narrow, so they're like easier to prove. But the Plonk gates are wider, but you can express more operations as a single gate. So in real life programs, it's a trade-off of like how wide of your gates you want to use. And Plonk, it's like you use a little bit of a wider gate, you can express more operations as a single gate, but because of that, proving each gate is a little bit more expensive. That's my hand-wavy explanation of how I understand it. And yeah, the actual Plonk gate is actually a little bit longer because it includes some other terms now. In Turbo Plonk and Ultra Plonk, it has some terms for lookup tables and for custom gates, but don't have time to look into how those work, because all this stuff is not documented anywhere. It's like, I have...
Seriously, no documentation?
Hmm?
There is no documentation in place?
No, so like when I was looking for that, like there are some blog posts that talk about that, they're written in a mathematical way. But generally, when I talk to the team behind Barettenberg about like, hey, can you tell me how your like gates work? The best way to understand it is to look into their C++ code, which sometimes has comments like that. And yeah, you read the code, you read the comments, and pray for the best.
To be honest, that's pretty common in blockchain.
Yep.
Kind of stuff.
Yep. Not complaining, just saying.
How long did it take to Ethereum to actually do proper disentangled? Remember Solidity 5 years ago?
Yeah, I was looking today for all the different versions of the header format from hardfork to hardfork.
Yeah, as well.
Nowhere to find.
Come on, there is not a single Ethereum client that has, a proper software engineering based manual documentation. Okay.
I think we're all on the same page.
Yeah.
Source code is the documentation.
Yeah. So that's why I don't understand how unsigned integers work, because it just takes a lot of time reading the compiler. So we'll show two real-life examples with what code actually like Noir provides and what circuits does it compile to. The first example will be for the Pythagorean triplet, so we'll check that a squared plus b squared equals c squared. And the second example will be for a simple if. So let's go to the Pythagorean triplet. So that's the code in Noir. Don't look at this title, I didn't change it. But yeah, it takes 3 field elements and it checks that x multiplied by x plus y multiplied by y equals z multiplied by z. And you see that it compiles to 9 gates, but 5 of those are kind of like reserved gates, something that compiler does even for an empty program. And here are the true gates. And we didn't talk about the witness, but the witness is very well explained on the Pythagorean triplets, because the witness is a trace of the computation in a way that in each gate we compute something, which is this output wire, and the witness is an array that like contains all those output values, so those partial output values up to the end value. So here we start with 3, 4, 5, those are our public inputs. But in the inputs later we have the output of this gate, which is 9, which is 3 squared, output of this gate, which is 16, which is 4 squared, and the output of this gate, which is minus 25, because it's on the other side of the equation. But yeah, so let's talk about those gates. Those gates, they operate on the wires, and the wires connect to the witness values. So here W stands for witness, and those indices are indices in this array. So let's ignore this Q arith because I forgot to delete it, and it's not very interesting here. But in general, Noir now, not Noir, but Barettenberg has some optimization for the arithmetic, and this arithmetic gate can have 4 different forms. And this Q arith by default is set to 1, and then it's like in a normal form in this known form, but other form are different. So the practical like polynomial for the gate is more because it can have also different values. But let's focus on this value of Q arith, of like vanilla Q arith. So we just take the first witness value, multiply, take it to the squared, take it to the second power, and say that it's equal to W3, but it should be on this side. So we just compute this 9 in this gate. This is essentially what this gate does. It computes this 9 by multiplying 3 by 3. The second gate computes this 16 by multiplying 4 by 4. So this is like the output wire for it. And those are input wires taken 2 times. So this by this equals this. And this computes this minus 25. It computes it in the minus because it moved it on this side. So
Maybe it's worth mentioning it's not really minus 25, but field max minus 25.
yeah, this is a simplification because if you actually print out those coefficients in Noir, they're huge. I can show them, but there are no negative fields on negative field elements, but I just do a trick like that. So yeah, so this is our prime number that we're using in Noir, and just if you have a -1, it's represented like that. It's just prime -1. So when we look, we can look at how, for example, the witness, not the witness, the circuit. Let's look at the if. Yeah, sometimes you have those like huge numbers here, which is this like prime field -1. whatever.
And this prime number is only one, or there is none?
This prime number depends on the curve that they use under the hood, and I think this one uses BN128. So this is just the number of elements on the circle that the generator on the BN128 generates. In different proving systems, they use different prime numbers here. Yeah, I think it's chosen because it needs to have some.
It's an interesting question. Is that the prime number?
Yeah.
And there's
Do we
no
wanna check?
syntactic sugar for this? Like you actually hard code the number yourself?
No, there is.
No,
It's-
you
it's what
in
you-
Noir you write
This
this.
is this. Okay.
So this is quite syntactic sugary. But yeah, I think in Circum, probably in first versions or in Halo 2, you used to do stuff more close to the bare metal. But yeah, we wanted to see, this is how it looks close to the bare metal, but I just wrote minus 25. Huh?
Very math even.
Bare math.
So what about overflows? So all of this stuff assumes we don't have an overflow, right?
Yeah.
All of the asserts and everything.
Except if you're using U32, then it has a range check and then it checks for overflows. Yes, correct?
I think so. Actually, I will just say I'm not ready to answer this question now. Because, yeah, well,
In theory, you could have had the prime number minus 2 as a real number. And you add something to it, and you don't want it to be like the minus 2. You want
Yeah.
No, I mean,
Right,
it's
so
in modular arithmetic is the same. You need
Exactly.
modular
So
arithmetic.
you would need to be doing range checks on every number.
No,
Like
pretty much.
probably.
whenever you
Every is exaggeration, but most.
whenever you intend to increment it, right? Well, or decrement it below
Depends
zero.
on the context, but yeah, in general, you always have to think about range checks.
Here the problem is overfilled elements, right? So you don't have overflows, you just like
No.
No, but I could have this.
Feature.
This sum could overflow, or like those multiplications can overflow, and then it will not be equal in classical arithmetic, but this can still be equal in modular arithmetic.
but that's how you define the problem here, right?
That's one approach to it.
Like you.
Do we have, yeah, Pythagorean triplets, so that is the separation, and we have this addition here, like W3 plus W4 plus W5 equals 0, so that's the final gate that combines those together and checks this equation. So this is the first program that's like does actually something, but it's still possible to understand the gate representation of it, because if you do anything with unsigned numbers, it's just a huge array of gates that are not possible to understand. And the second problem that is still kind of possible to understand is an if. So we do have x here, and I substituted x equals 1 for this program. And I did if x plus 1 equals 1, then x equals x plus 2, else x equals x plus 1. And at the end, I asserted x equals 2. So if we do 1 here, then this is false, else is executed. And then we get 2 here, and it actually equals to 2. And I splitted those gates into 2 because the screen size, but yeah, gate 6 goes after gate 5. And if you compile this, you see that it generates 13 gates. We remember about 5 gates that don't exist, and we get 8 gates as we get here. So here's the witness for that. And if we remember how we can compute the if, we compute, we will talk about this from the end, but in general, we compute the predicate, we compute 1 minus predicate, we compute the then, we compute the else, and we do a linear combinations of those together. So let's go from the end. Here, we check the equality of like 2 equals 2. This is the constant, and we check that this W7, this is 1, 2, 3, 4, 5, 7. 6, yeah. So this will equal to 2. But then those multiplications actually compute the then multiplied by predicate and else multiplied by minus predicate. So we can see that this is 4 multiplied by 5. So here 0, 1, 2, 3, 4 multiplied by 5. And this is 2 multiplied by 3. So this is the value of the then. This is 3, which is 1 plus 2. So this is the then value. This is the else value. So it's 1 plus 1. This is if else is enabled, if else is executed. This is if then is enabled, if then is executed. And then we take this multiplied by this, which is the value of the then, this multiplied by this, which is the value of the else. And yeah, we combine them together to check them with 2. So yeah, this is multiplying those by predicates. This is actually computing those then and else. And somewhere here we check the predicate in those gates. I think this is this. So we can see the witness for this if contains all the intermediate variables, and this is the gate representation of the if in the simplest form. And this is all that I have for you today. If you have any questions, feel free to ask. If you have any programs that you want to compile and see the gate representations, we can play with my code and see if someone is interested, how does this get compiled. But most probably we won't be able to understand it on the fly, but we can try.
I have a question. So what is a possible way to attack a circuit?
What is a possible way to attack a circuit?
Yeah.
So I think the simplest one is when we don't check something in a circuit.
Okay.
For example, fun fact, there was recently a vulnerability in Noir that just got fixed. So when you return the unsigned number from unconstrained code, it wasn't doing a range check. So for example, the attacker could have returned something that's not within the range from the unconstrained code, and they just recently fixed it because the fun fact, the way they fixed it is I was playing with some library and I saw that it's cheaper for me to do an addition in unconstrained code and then check it with multiplication. And I submitted the PR to this library being like, hey, you can use this optimization. But then the guy from the compiler, Tom A. French, I think, went there to this PR being like, this is not cheaper, this is not correct because of my issue. So yeah, because they already do this optimization in the compiler, I thought maybe I can introduce this like division and unconstrained optimization in the compiler, but the compiler is pretty smart and it does this under the hood. But because this was an unconstrained code, they weren't checking, they weren't doing the range check at the end.
But also you can show when you made a bug on the slides when you didn't do one check. Right?
Yep.
The one that Arek found.
It's always better to show my bugs than someone else's. So here we also don't do the check that this in fact is a bit representation of this number. And this also should be B. This is the first one, so like you don't check stuff, and because of that you can prove, it's not that you can prove false, but this is like in Solidity, like code is law, you can prove that something satisfies those constraints, but what are those constraints? Because in fact, you want to prove facts from real life, but you prove them on the proving system that can only prove additions and multiplications, and real life is not additions and multiplications, so in this translation phase, a lot of things can get lost, like in the DAO hack.
So a general question. So you said that you are using Loire for the SHA-256. Why not Circom? That tends to be more powerful. I mean,
Did you try writing in Circom?
Hmm?
Did you try writing in Circom?
I actually use a Circom and not Loire, so
Okay. So it's you need to write single gates, right? In Circom. In Noir, it's like a language.
But then you gain in performance. So
Not so much.
okay.
Not so much. Noir is now kind of already. I believe I might be exaggerating, but I think it's in par with Circom already, which was not the case 3 months ago.
So
we believe in the long run, it's gonna be.
Because the last time that I touched it was 6 months ago, more or less.
Very different language.
Okay.
I tried to look into like maybe I can implement Ketchak better in Noir, and I tried to look into how Noir does Ketchak, and they have a lot of code making it optimal. So they have the lookup tables there that are used. They have the custom gates, and they reduce the cost of Ketchak a lot in the different in the last half a year. And yeah, because we wanted to focus more on developer experience and we wanted to leave that stuff to Noir team, because it's not only up to us to implement optimal Ketchak, but like everyone needs it, and they are actually working on it, and they have people who are much better in math and that than us. So we decided to go with a language which has a better developer experience, and under the hood, this can be optimized by the language team.
Also, the Ketchak implementation was done by Zach Williamson, who we probably won't be able to look after in circle on the one.
Yeah.
And do you know, like in general, how the lookup tables work? Because it's like helping a lot, but I don't know how this could work because you can't have lookup table for every hash or something. That's what I'm thinking right now.
Yeah, so the way I understand the lookup tables is that you have some functions which are hard to impossible to represent as pluses and minuses, but those functions are functions on the limited domain, and you just compute this function for each domain element, and you then have a table which says that for this domain element and for this codomain element, this is actually the result, and there is a 1 there. And then you compute the polynomial, which checks that like there is you like take the index here, and that there is a 1 on the intersection. This is a very hand-wavy exploration, but
I think one example I can give you.
so
Don't have a lookup table for, let's say, a whole catcher because it's too much, but you've got a lookup table for the simpler like building blocks, right?
Yeah, so for example, imagine you have AND function, logical AND, right? So you could just build a table for, let's say, U4, right? And that has 0, 1, 2, 3, 0, 1, 2, 3, right? And then all the values of the AND operations for those, right? And then you can slice like Leon showed, you can slice a non-constrained code, let's say U32 into array of U4s, and each you can calculate from the lookup table, and then you can just connect them with very cheap multiplication and addition operations. And this is, I believe, this is actually how lookup tables works in case of.
But where is the lookup table like located? It's on the prover side or something? Do we trust the values in the lookup table?
Yeah, it's kind of, you can think it as about as a custom gate, let's say. Right? There is a gate that already verifier and
like
prover kind of pre-agree.
Yeah, so this is like a common on the protocol, on the verifier
Yes,
prover side.
yes.
Okay.
But the problem is you kind of need to put them somewhere in memory of the prover, right? So it would be hard, for example, to do U32 lookup table. That would be like 4 billion by 4 billion.
So the way
So this works well for AND, but not for hash, right? Because you can't split hash into
No, I mean it can work for hash in the sense that Kajak is made of bitwise operations. Yeah, but because Kajak used a lot of bitwise operations.
So actually in Rottenberg, in Plonk, you have more selectors than we talked about. We talked about multiplication, constant, left, right, and output selectors. But they also have something like Q8, Q sort, Q elliptic, Q auxiliary, which I don't know what they're used for, but I guess they may be like references to elliptic to the lookup tables, or maybe they're used to implement some other operations more efficiently. In all of the programs that are compiled, those were 0. So we can look like at the circuit, and this is like the first selector, the second selector, there's like Q and QC. And all the selectors at the end are 0s, so they're not enabled, but maybe if I write some more complex programs, they will be not 0.
Any more questions? If not, then thank you so much, Leon, and it's pizza time.
It's also the notebooks time.
Oh yeah. Who won?
Oh, thank you very much.
Well, thank you. Thank you.
The selection was totally arbitrary, don't get offended.
Jest po prostu. Jakby
specjalnie przygotowałem na to, żeby